moment to turn in the Kinematics Homework 1 if you haven't already done it. I'm going to ask that you turn in a paper copy of that as well, but you don't have to do that yet. I want you to turn in a picture right now if you haven't already done it, and then we're going to go through at least one or two problems, and then after we've gone through the problems, so that way you can look at your homework while you're going through the problems, then I do want the paper in the video. And let me tell you the deal with homework. So I am giving you just like you get 4 points sometimes for doing the homework. It's not going to be a huge hit to your grade if you miss one or two. It's not going to be a huge hit to your grade if you're late every once in a while. Here's what will be a huge hit to your grade. If you either don't do the homework at all, so you just really don't know what it looks like and you haven't tried it yourself, or if you do it in 3 minutes right before class, scribbling things down, potentially while looking at somebody else's work for guidance. And the issue here isn't that you, I'm not concerned about the morals and ethics of using somebody else's work to get points. I'm telling you that if that's how you're doing the homework, you aren't practicing the problems, you aren't actually learning anything from it. I would say for the majority of students in physics, the single biggest barrier to their grade, and if this isn't like, I mean, these are students that pass the class, but the biggest barrier to people's grades is that they watch me do stuff and they think, okay, I got it. And what they don't realize is that watching me do stuff and being able to do it quickly and efficiently themselves are two different things. And Tracker is a great example of that. I can't tell you how many times people have watched me do Tracker and thought, this is not hard. And then when I give them a video, they can't do it. So just be aware that that is something that happens. It's not necessarily going to happen to you, but what I would say is do the homework, turn it in. If you didn't do it last night, don't try to scratch down a bunch of stuff to get the 4 points. Do it over the weekend, turn it in. It'll be late. It's no big deal. You'll lose points. No big deal. You're better off losing 2 or 3 points on a 4-point homework assignment than you are losing 5 or 10 points on a 40-point exam. And that's what'll happen if you don't know how to do the problems. Some of you, in all honesty, aren't going to have to do the homework. You can hang on to it if you have questions. You don't have to, but I'm going to go through it real quick. And the thing is, if I knew which of you was in that boat, I would just flat out tell you that. I would say, you and you and you're not going to need to do the homework, but you and you and you. The problem is I don't know. And you might be able to figure it out on your own, which would be great. I'm not going to be critical if you're not doing it and you don't need to. But again, my experience has been that a lot of the people who think I don't need to do this, think that because when I do a problem, it makes so much sense and it looks so easy and they're like, okay, I can do this, but they can't necessarily. So do that practice. All right, so today we've got a few things that I'm gonna do and then some stuff that you're gonna do. For announcements, first, if you're done taking your picture, will you close your Chromebook? And then next, don't forget, Monday is going to be a quiz over Tracker. And I'm going to show you what you're going to need to do today. You've seen it already. And for today, the demonstration, I've done a shortcut that I'll explain. But what the interpretation and the analysis that I do today is going to be really similar to what I asked you to do on the quiz. The quiz will be a file posted to an assignment that you can download, and you'll put the numbers, put the dots in, and do the analysis on your own with just your Chromebook. And so what I'm about to show you is what you're going to need to do. And then looking even further, on Monday the 20th, we're gonna have another quiz. This time it's gonna be a one-dimensional kinematics problem. If you did the homework, it's gonna be similar to like the two that were in the problems section, or those basic kinematics practice problems that I gave you, where you're finding one of our kinematics variables for an object that's only moving in a straight line. It is not moving two-dimensionally. So today we're gonna start talking about two-dimensional motion. That will not be on the quiz for next Monday. Okay, so first, does anybody have any questions about any of that information? And second, let's talk about the homework. So I'm gonna what I wanna do is talk about number 8, question 8, and problem 33, problem 30. Problem 30 and problem 33 are really similar. And so if you can do 30, which I'll do for you today, then you will be able to do problem number 33 as well. And then 8 and 9 are different, but I want to focus on 8 because there's a couple things in there that are actually kind of important to think about. So for those of you who didn't see it or forgot, number 8 says a ball is thrown straight up into the air, so into the air and back down. At each of the following instance is the ball's acceleration equal to g, negative g, 0, less than g, or greater than g. And the 3 instances are just after leaving your hand, at its very highest point, and just before hitting the ground. So here's the backstory to this. What I told you is that in free fall, things accelerate at a rate of 10 meters per second squared toward the ground. That's the direction that it goes. If you define an axis like the y-axis as being perfectly vertical in the Earth's gravitational field, and you say that up is positive, then that means that you can use a negative sign to indicate the direction, which means in that frame of reference, things will accelerate at negative 10 meters per second squared toward just period. That tells you the direction if your reference frame is a vertical line that is in the direction of the Earth's gravitational field. The problem is you don't have to do that. You could say that straight down is positive, in which case the acceleration would be positive 10 meters per second squared. Or you could even, and you don't have to understand this now, but we will talk about it down the road, you could set up a set of coordinate axes at right angles to each other that are not aligned with the Earth's gravitational field. And in that case, down isn't positive or negative. Down is in this direction, and if this is the reference frame that we're using, then we would need to express its direction relative to one of these axes. So I might say 8 degrees to the right of the negative y-axis or something like that. That's the direction. It's not positive or negative anymore in terms of its direction. It is at an angle to a coordinate reference frame. So the book is saying like this negative stuff. What the book is doing is something that is okay to do, but I'm not going to do it. The book is saying that in the absence of any other information, you can assume up is positive, down is negative, to the right is positive, to the left is negative. A standard Cartesian coordinate system that is parallel and perpendicular to the ground. That's okay. You can do that. It's just that you don't have to. And so that's one thing that's important. What they've done in this problem is they made that assumption, and then they assume that you're going to make that assumption as well. The second thing is instead of saying 10 meters per second squared, they're using the constant g. So this will come up again and again and again. So everyone should listen to this. G is defined as a positive number. G is the magnitude, I love it, G is the magnitude of the acceleration of an object in free fall. It does not include a negative sign because it doesn't include direction at all. And even if it did, how does it know what your reference frame is going to be? G is positive 10 meters per second squared. So if we say down is negative, then that tennis ball is accelerating at negative G the whole time it's in the air. Immediately after it leaves your hand, it's accelerating toward the ground at 10 meters per second squared. At the top of its arc, accelerating toward the ground. Right before the ground, accelerating toward the ground. The answer is negative G for all of those. Now, had you said, well, I'm going to define the downward direction as my positive direction, then you could have correctly said that the acceleration was G in all cases, because then your direction is positive, and positive G is positive 10. And that gets, that seems like it's sort of trivia, but what's going to happen is we're going to use that constant G a lot, and many of you are going to ask me at some point in the next 6 months, wait, isn't G negative? And it's not. G is defined as a positive number, which means if you are using a reference frame where this direction is negative, you have to put a negative sign in front of the G to make the acceleration of an object in free fall in the right direction. All right, so it's a weird one. You'll get used to it, but sometimes it takes a little while. Okay, so first, does anybody have any questions about that? Okay. Second, I'm going to do problem number 30, and let me just tell you that yesterday, so I can't see as well as I used to, and so I solved problem number 33, but I misread it, and so I solved it basically I set it up incorrectly, and then things went downhill from there. So if you see me do something, you can raise your hand, but also feel free to bark out. It's not this, it's that. And if you're wrong, then we'll figure it out. But if I'm wrong, then that'll make the course correction a lot easier. I know these problems really well, but I haven't looked at them for a year. So just be aware that I might make a mistake in the way that I set it up, because it's hard for me to look up and down and read and write and look at you all at the same time. And I'm going to do the math. I do a lot of the math mentally, which is not a good idea because I make a lot of mistakes. I just don't care. You might care more than I do about mistakes that you make. So you use a calculator, and if I do something, you can check my work. It's fine with me if you have your calculator out and you're checking my work as we go. All right, so in this problem, we have a flea, and the flea rapidly extends its legs. So here's what I think a flea looks like, and in this case, the flea has legs. So I'm going to draw the flea's legs, and what's going to happen here is the flea's legs are going to go up. It's going to move up. So the flea is going to start here, and it's going to end here with its legs fully extended. Okay, so this is the flea after its legs have spread out. And we're going to do a whole bunch of stuff here that's not entirely accurate, but that's actually pretty reasonable to think about. So it rapidly extends its legs. It reaches a takeoff speed of 1 meter per second. So at this point in time, it's moving upward at 1 meter per second. Initially, we can assume that it was at rest. And it does that over a distance of 0.5 millimeters. And I told you that I'm not going to make you do conversions, unit conversions, but somebody else might. This is an example where somebody else might. 0.5 millimeters is, okay, checkmate here. I think it's going to be 0.005 meters. No, there's another zero, isn't there? Yeah, 3 zeros and then a 5. 3 zeros and a 5. So that's a stupid number to use, but That's what we've got. This is my picture. My reference frame is going to be that up is positive and the ground is position 0. And I'm going to use y for my position variable because it's a vertical axis. You could have used x too. There's no rule that says you have to use y. In this case, just that sometimes you will. So the next step is to list my variables, y0 and y, v0y and vy, a, y, and t. And the question is asking, what's the acceleration? And some of you might be like, well, it's negative 10 meters per second squared, but it's not, because it's not in free fall. It's pushing itself up with its legs, so it is not unsupported in the Earth's gravitational field. So let's put in our variables and see where we get. Our initial position is the ground. Our final position is 0.0005 meters. And some of you might be like, but wait, it sort of stretches out, like it's still on the ground. And you're right. And this is one of the assumptions that we have to make is that the legs, while they're in contact with the ground and while they're pushing, are mostly massless. Like most of the flee is up here, and only a little bit of it, a part that we can ignore, is in contact with the ground. That's not 100% accurate, but it's good enough. Our initial velocity is 0 meters per second. The final velocity is 1 meter per second. We don't know the acceleration or the time. If we were to look at our variables and our equation list, what we would see is there's only one equation that has acceleration without also having time. And so the first and the second one both have time in them. You don't need to have these equations memorized. I'll write them down for you, but I have them memorized. So I like, if you don't have them memorized, you can look real quick right now, if you didn't already, to verify that the first, second, and fourth equations that I gave you all have time in them. There's only the third one that doesn't, and the third one looks like this. V squared, oops, that's not squared, V squared, and I'm using a y here because I'm using the y-axis, so it's not Vx squared, it's Vy squared, equals initial velocity in my y direction squared plus 2 times my acceleration in the y direction times my displacement. And if this were a test or a quiz, some of you might be like, well, what do we do? Like, can we use the solver? And the answer is no. I'm not going to let you use the solver on a test or a quiz. So you have two options here. If you have the algebra skills, solve it. And I'll show you how to do that in just a second. If you're not strong in algebra, then you can get full credit by saying, I would choose this equation in the solver and select A for the variable. That's good enough. It isn't ideal. Ideally, you would all have the algebra skills to solve a problem like this, but I know that that's not the case. So just like understand that I'm not going to make you do algebra. If you want to learn algebra, you can, but I'm not going to be able to teach it to you. So I'll show you how I would solve this problem. Those of you who have the algebra skills should solve it this way. So first of all, I always solve for the variable that I'm looking for before I put any numbers in. I am looking for this. So I'm going to solve this equation for AY. And so that's going to be Vy squared minus V naught Y squared. Vy squared minus V naught Y squared. All divided by 2 times the displacement. And if you don't have those algebra skills to do that in your head, but you could show your work, great. But if you can get from here to here without making a mistake, you're fine. If I were taking a test, I wouldn't do it like this, because I wouldn't trust myself to do it right. But I'm doing it like that for you. Now I'm going to plug in my numbers. So my initial velocity is 0. My initial position, you can't see it, but it's 0. So this is going to be my velocity squared, 1 squared, divided by 2 times my displacement, which is 0.0005. And one thing you'll see here is I'm not putting the units in. That, again, is purposeful. I put the units in my variable inventory and on my picture because I want to make sure that the units are right. As soon as I get an equation, I leave the units out. I'm going to trust that the equation would reduce the units down to what they should be. I'm not putting them in because it's too easy to get units mixed up with variables, particularly m, which is the unit for meters. It also is the variable that we're going to use for mass. That gets really weird when you see an m in an equation and you don't know if that means meters, which is a unit, or mass, which is a variable. So just leave out those numbers. And this, as you all know, is equal to, I don't know what it is. Will somebody tell me? I can't do that. What's that? 1,000 meters per second squared. I didn't trust myself to do the mental math. Okay, so there's your answer. Not only is this the right number, but it has the right sign as well, because we put all the, if there had been any negative directions, we would have put those in. And so this is the correct sign. And sometimes the question, like in problem 33, it asks for the magnitude of the acceleration, and I hate that because what that implies is that if you put a negative sign, you'll miss the problem, and that's what people do that on purpose. They want you to miss the problem, but I don't. So I'm not going to ask you for magnitudes. I'm going to let you do the science, and if your answer includes a negative sign, just put the negative sign, and for any vector quantity, that will indicate direction. We can now find the second part of the problem, which is time. We can do it in a variety of ways. Now that we know the acceleration is 1,000 meters per second, any of the 3 equations that we didn't use will give us time. In this case, the easiest way to do it is going to be to use this equation. Final velocity is equal to initial velocity plus acceleration times time. So that means that time is going to be equal to final velocity minus initial velocity divided by the acceleration. So that's going to be 1 minus 0 divided by 1,000. And I can figure out that that's going to be 0.001 seconds. Did I mess up any of my math or my algebra here, or does that look right? If I messed it up, then the point is, don't take shortcuts like I did, right? But the physics here is correct. All right, so if you haven't already, will you pass the homework forward, put it in the bin, and then we're gonna do a couple other things real quick. I want to first, as promised, go through a quick tracker demonstration. Yeah. Like I told you before, I have set this up already with some stuff that you should know how to do. So don't assume that the problem that you get on Monday is going to be half finished for you in Tracker. I posted this video for you all as a practice. It wasn't homework, but hopefully you did it, or at least looked at it. Here's where I got. So basically what I did already is I found the place where that ball leaves my hand, and I set the time equal to 0. I set up my calibration stick and I set up my coordinate reference frame. I made the ground position 0, right where the ball lands. And then I plotted the points, and I put all of them. It went down, and then it came back up again, and then it went part of the way down, and I got all of those points in there. So what I want to do with those prompts asked were, number 1, how fast is the ball going right as it leaves my hand? Number 2, how fast is the ball going right as it leaves the floor? 3, what is the acceleration on the way down? 4, what is the acceleration on the bounce? So all of those, we will analyze this parabolic curve in the vertical dimension. My x dimension, it looks like the ball when I dropped it drifted ever so slightly to the right, but we don't care about that. There's nothing interesting going on there. It's the y dimension where we've got some interesting motion with acceleration. So I right click here and choose Analyze, and then the first thing that you will see is it analyzes all this data and tries to come up with a single parabolic curve to fit it. And that it did. And it actually did a really good job of it. This is as good as anybody else could do. It just doesn't mean anything, because a parabolic curve is like the curve formed by a quadratic equation. And this is not one quadratic equation here. It's 2. There's one quadratic equation and parabolic curve from when I drop the ball to right before it hits the ground. And then there's one quadratic equation and parabolic curve after it hits the ground. Both of those time periods involve constant acceleration. It's the same in both of them. It's accelerating at a rate of 10 meters per second squared toward the ground. But when it hits the ground, it's no longer experiencing an acceleration of 10, nor is the acceleration constant. So there's a time period here that just isn't really, we can't really interpret this or analyze it. There's a lot going on right here. So if I want to think about what's going on in either of these sections of motion, I have to highlight just those points. So let's do that. I'm going to highlight, that was a terrible way to do it. I'm going to highlight the initial parabolic curve points. I'm leaving this stuff out because this part on the ground is a little weird just because it's not accelerating at a constant rate down there. I don't know exactly when it hit the ground, and so I'm just going to leave that out. But you can see here, now I have a parabolic curve that fits my data basically perfectly. I mean, that's as good as you're going to get. And when I look at my parameters, here's what I see. My A parameter is negative 5.2. There's no e to the anything, and so that is a oh shoot, that's really interesting. Hang on. That's super interesting. So it has the wrong time. Do you see that? Let's see if I can get this to switch. Okay, hang on. I have to, this is, I saved this and reloaded it. So this is an unfortunate tracker bug going on right here. How do I deal with this? Let's try this. I think this is going to work at some point. It's going to take. Nope. Drats a lot. Okay, hang on. Sometimes you have to really there. Oh, thank goodness. Okay. Sometimes you have to really finesse things with Tracker. Okay, so let's try this again, and I think we'll get better information. Yeah, okay. So we have the same A value of negative 5.2. To get the acceleration, we double that. That ends up being negative 10.4. Negative is down with this reference frame. So that means my acceleration was 10.4 meters per second squared toward the ground. That's pretty close to G. That seems like a reasonable acceleration. My velocity at the start is negative 4.8 times 10 to the negative 1, so that's about negative 0.5, about a half a meter per second. Is that right? Well, I mean, yes, in that, like, the ball left my hand and then it started speeding up, and so it did hit a half a meter per second at some point there, going down. We know that right as I let go of the ball, its velocity should have been 0. But since this video was shot at 30 frames per second instead of 1,000, it looks like it sort of missed some of that information. Like the first frame, the ball was probably already moving a little bit. So negative 5 meters per second is a reasonable velocity for a ball that's just starting to fall, okay? Now let's look at the second set of data. And for this one, again, we have to be a little bit thoughtful about how we do this because yeah, that's probably okay. That's not what I wanted though. I wanted to start here. Let's see if we can do it this way. I'm gonna get a little bit less data. Okay, that's good. That seems like this is reasonable. So again, the second part of the data, that's a really good fit, and our acceleration is twice negative 4.7. So that's like negative 9.4, so pretty close to 10. Is it the same? It's not the same number, but they're so close, and they're both so close to 10, and we know it should be in free fall. So yeah, this has the same acceleration during both parts of its free fall motion toward the ground at 10 meter per second squared. My initial velocity here says 8.1, but that is not the velocity right after it left the ground. That's the velocity that it would have if this parabolic curve were extended until it intersected with my y-axis. Time equals 0 is way down here. This 8.1 meters per second reflects the speed that this ball never had. It would have had it if it would have started at time 0 and gotten to this point at time 5, but it didn't do that. It started at time 0 in a completely different location, and it accelerated really rapidly over a short period of time to get to this velocity. So to get that information, we have to go back to our main table or our main window, and I need to set this point right here. I do that every time. I need to set this point right here. I'm going to say maybe like right there. It looks like it's you can tell it's on the way back up, right? So it bounced. It looks like it's on the way back up. I'm going to set that to 0, and we'll see what we get. And so I clicked on an advanced frame just because of a weird tracker bug. And now when I go to the Analyze menu, it hasn't updated. It's still got my time 0 on the left. Oh, and now it like updated. My time 0 is on the right, but it changed all the points that I highlighted. Never fear, I can just do all that again. So there's my graph. You can see the acceleration doesn't change, which is what we would have predicted. But now the initial velocity is showing us the initial velocity at time 0, which is now right here, which is right where we want it. So the initial velocity of the ball as it was just leaving the floor was somewhere around 3.5 meters per second. This is 3.35, so somewhere around there. That is what you're going to need to be able to do with tracker. So any questions about that? Okay, the last thing that I want to show you quickly before you have some time to work on the assignment that we started last class period is something that I created called the vector solver. And you'll need this potentially a lot, especially if you're not a trigonometry person. And so if you click on the vector solver, it pulls up this Google Sheets spreadsheet, and then you'll need to make a copy of it, which I've already done. And what the vector solver allows you to do is, well, several things. One is you can put a vector magnitude and a horizontal angle in, and it'll tell you what the x and y parts of that are. Most of you have seen this in the simulation that you were using on Wednesday, but just in case you didn't, here's what it looks like. Let's say that I put a vector in, vector B, has an overall length of 11.2 at an angle of 26.6. If I put that into my vector solver, 11.2 for my magnitude, 26.6 for my angle, and then I indicate that it's pointing up and to the right, it tells me that that is horizontally 10 units to the right and vertically 5 units up. When we look at the simulation, if we put those components in, we see that that is indeed the case. 10 units to the right, 5 units up gives us a overall vector of 11.2 at a 26.6 degree angle. And then we can also, with the vector solver, put things back together. So if I can kind of check this, right? Like if I have a vector that goes 10 units to the right and 5 units up, then it tells me that my magnitude is 11.18 and my angle is 26.56. We don't, like, there's a lot of rounding going on here, isn't it? This is pretty close to 11.2. This is pretty close to 26.6. So there will be a point in the vector simulation activity where you'll need to do some of that checking for me, to use the vector solver to check, like, not check, but just like see how this mathematical tool matches up with this graphical tool. They tell you the same information. This is not a useful thing to use when you're solving problems, because you can't pick vectors of any length and they can't be in like different, like it's constrained. The mathematical one, you can put in a vector of any length, you can put in any angle, you can go to up and to the left or down and to the left, down and to the right, and it'll correctly break it down into the components that you need. Alrighty. So I'm gonna give you some time now to work on the vector simulation activity, and I'll give you, we'll just kind of see. I have a few more things that I want to discuss in the presentation that we started on Wednesday, but I'm going to give you some time to work first. Now is also a good time to take a break if you want one. And then as we get closer to the end of the class period, I'm going to take over, talk to you about this a little bit, and then if you're done with the vector simulation activity, there's something else you can work on. And if you're not done with the vector simulation activity, you can keep working on it. Okay? All right, take a break if you need one. Let me